Hey, so we we were looking at iterative methods. We looked at Jacobi iterative method, which basically takes the equations, rewrites them, and then as x1, x2, so that you take the diagonal element to compute x1, x2, and then iteratively solve for the solution. This one, we did 3 iterations, but we eventually figured out that it takes about 500 iterations to actually converge. Then we looked at an improvement over Jacobi method, where instead of trying to update each and every value for x1 after every iteration, you just update the best value, the previous, just keep updating the value as you find it. So for example, here, if for 2 equations, 2 unknowns, we computed x1 iteration 1. Why not update x1 in that same iteration? And we did that for the same problem. We did 3 iterations, but it did not converge. But when we went to the code, we saw that it converged in about 17 iterations. So we went from about 500 iterations in Jacobi to just 17 iterations with this method. So this method we're going to talk about today for first half of the class is known as the relaxation method, which can further improve how fast the Gauss-Seidel method converges. Remember, the Gauss-Seidel was the one which converged in 17 iterations. This is claiming to be faster than that. The update rule for this is the following. We have the estimate at step i+1, iterate i+1, is going to be the weighted sum of the previous iteration and the value obtained from Gauss-Seidel. So the Gauss-Seidel, you just do it as we did it previously, but instead of using entirely an update based on Gauss-Seidel, so if you do w equals 1, right, this will become 0, right? Then you have a Gauss-Seidel update. But if you choose any value which is not equal to 1, then you will basically have a weighted sum of updates. Now, this w is a user chosen constant. Okay, you would choose this based on the problem at hand. It's typically between 0 and 2. If you choose it to be between 0 and 1, it's called successive under relaxation, SUR. And if you choose W from 1 to 2, it is called successive over relaxation. SOR. Okay, a simple update. Okay, so what we'll do is I will show you if this is indeed going to make things go faster for us. So I'm going to take the same problem, which we solved using the 2 methods, and solve it using this particular method and see if it's any faster. So the problem is, I'm just going to copy this off here. It's the same problem, but with a different method. Okay, so solve for x1, x2, x3 using relaxation method. Use the initial guess of zeros, solve up to 3 iterations, and then we'll use I will also put it here, w equals 3. Sorry, w equals 0.8. Okay, w is the user chosen quantity. Normally, you would have to do it yourself, but let's say that we're given it's 0.8. Okay, so here's how we proceed. Just like before, we'll solve for x1 from the first equation, solve for x2 in the second equation, solve for x3 from the third equation. Okay, that looks about right. No, this is incorrect. Yeah, this is also incorrect. Looks about right now. Okay, so what we're given is x10 equals x20 equals x30 equals 0. Okay, let me copy this. Okay, I would need that every iteration. Just for reference. Okay, you all ready? So iteration 1, x1 equals 7 minus 0 divided by 2, that is 3.5. Now what I'll do is the following. This is my value at iteration 1. I'll put a bar here just to indicate that's the Gauss-Seidel computation. It just it'll help me. So this is my Gauss-Seidel value. So at this point, everything is from what I've done here is the same as Gauss-Seidel. Now, the update rule we're talking about for iteration 1 is 1 minus W iteration 0 plus W iteration 1 from Gauss-Seidel. So that would be 1 minus 0.8. We know the value at 0th iteration is 0 plus W is 0.8. X1 is 3.5. So this will come out to be, I think, 2.8. Yeah. Okay, next, x2. Again, I'll put the bar to indicate this is my Gauss-Seidel value. Iteration 1 is, I'm going to use this formula here. And then the other one was this formula. Okay, so using that formula, we have -2 minus x1. Now, when I have this x1, I need to use the improved value, which is 2.8, minus the value at iteration 0, which is 0, divided by -3. Okay, so that comes out to be 1.6. Okay. Now that we have that value, let's use the relaxation method to compute x21. It's 1 minus W x20 plus W x21 with a bar, just indicates the value from Gauss-Seidel. So 1 minus 0.8 times 0 plus 0.8 times, this is the new value, 1.6. So it's 1.28. Next, we go for next we go for x3. x3 bar 1 equals, we'll use the third equation. So that would be 3 minus twice x1. So now this will be x1 at iteration 1, which we have computed to be 2.8, minus 2 times x2, which is a new value, 1.28, divided by minus 1. See, so what this comes out to be is I get 5.16. Okay. And then if I do the SOR, I get x3 1 equals 1 minus w x3 0 plus w times x3 Gauss-Seidel. So 1 minus 0.8 times 0 plus 0.8 times, this is the value I get from Gauss-Seidel, 5.16. With 0.8 times 4.128. So what we've achieved after one iteration is this particular set of values. x11 is 2.8, x21 is 1.28, x31 equals 4.128. Okay, so that's the value after one iteration. You need to do that for iteration 2 and iteration 3. So I'll not do that. I'll give you the answers for that. For iterations 2 and 3. So I'm going to give you a table of values, and then you can check yourself. Check your calculations with the table given below. Iteration number x1, x2, x3. What? Let me just do it this way. 1, 2, 3. What I got is 2.8, 1.1968, 0.6055. For x2, the values were 1.28, 2.2093, 0.1701. x3 were 4.128, 3.8753, then 2.8160. Okay. Yeah, they said this is very cumbersome to do by hand. So what we'll do is we'll write a code, or rather modify the code. It's much easier from the Gauss Seidel. It doesn't look like a big change here, and then see if we can reproduce these answers to 3 iterations. And of course, we'll see how many iterations it takes to converge. The convergence for this is something like you will try to see if x1 is not changing or x2 is not changing between iterations. If it's not changing by much, by let's say if we say a tolerance of 1 e negative 3, if it doesn't change in the third decimal place, I say it's converged. Now you need to do that check for each of those 3 values, or you could use the sum of squares of these values to be the tolerance or the place when you stop. Okay, so that's that. Let's look at the code. This was some of the code I had from last time. It basically does the Gauss Seidel. It's on the same problem. So you can see these matrix should be the same as what we have. So we're just going to modify this. Seems like much easier to do than to try to write your own code or use ChatGPT. So what I'm going to do is we'll take the Gauss Seidel, make a copy, and then let's rename this. Relaxation. Okay, and let's open this. Okay, now this has to be renamed. It should be relaxation. And then this one has to call relaxation. Okay, and then okay, now I'll run this, and clearly this is going to produce the solution, even though it's called something else. I've not modified any codes, which means it will just solve for the same thing I've written it for, which is the Gauss-Seidel. Okay, so run this. So change directory, and I'm moving. Okay, it's moving. Okay, so this is basically starting off as Gauss Seidel. It's basically converging to 1.002, 2.006, 3.005. The tolerance is 1 in negative 3. So the first 3 decimal places, it is spot on, right? I'm not just 4th decimal, no, it's not accurate because that was not my tolerance. And then it takes about 70 iterations. Let's try to modify this file now. So if you look at this file, the relaxation, we originally had Gauss Seidel here. What needs to be done here is we need to obviously supply the parameter w. Without w, it cannot update. So this function is missing that. So let's do this. Let's define a parameter w, and in this case, it's 0.8. Let's pass this value. So we have to choose a place to pass it. I don't know. Let's pass it, let's say, as the 4th argument. So 1, 2, 3, 4. Go to relaxation, pass it as the 4th argument. Okay, now we have that w. We just have to use it in the code here. So remember what relaxation does. It does the following. This is a comment. X new would be x previous, sorry, 1 minus w times x previous plus w times x cos theta. Right, we're trying to reproduce this. We know that this value here is actually the x cos Seidel. Cos, right? That's the Gauss Seidel value. And then we have x previous is nothing but x new I. Okay, so the x new would be 1 minus w times x previous plus w times x cos Seidel. I think that should work. So every time I have a new x new, which is based on the previous one, and why is x new the previous one? It's because if you see the way I've set it up, I say x new is x0. So x new is the previous iteration value, and then that's being updated every single time. So I think this should work, and then set it to print the first three values. So if I run this, hopefully it'll work. Okay, so if you look at this code, oh my God, I have to move this up. Won't move up. Maybe now, okay, there's a glitch there too. Okay, so when I run this, first of all, notice that the table we generated, that by hand calculation, is probably exactly this 2.8. I'm just taking 1.28, 4.128, yeah. And then the second row in that was 1 point, yeah, this looks right. And then third, yeah. So this values for the first three iterations are exactly what we got from hand calculation, which is a good sign. What we did by hand and what we wrote code makes sense. If you look at the conversions, you can see it's 0.9995. That's actually accurate to 1e negative 3 decimal places, right? So that's all good. And then the best part is the number of iterations. It took 12 iterations for this to converge, while Gauss-Seidel, which I have over here, this is Gauss-Seidel. I think if I run this, it will not run though. Oh, it ran, okay. Sometimes it gives me the glitch, I have to restart. Anyway, it solves this problem in 17 iterations, but the relaxation goes only 12 iterations. Now, I could play with this. I could play with the weight. I could try, by the way, if you try one, what do you expect? It's the same as Gauss-Seidel, right? Because if you look at the formula here, if you put 1, this will be 0, so it will be Gauss-Seidel. So I'm expecting it should converge in 17 iterations. Let's see if that's the case. So it's 7 iterations. So that's just another sanity check that the calculation makes sense. If you can go 1.5 and see what happens. There was a problem. I don't know what the problem is, but clearly it went out of control. Not a number. Try 0.1. 93 iterations. Try 0.99. 16. So it looks like it is at 0.8 it was 12. At around 1 it is 17. If you go very low also it is high. So it seems there's a sweet spot between 0 and 1. And we can try that out. We can try a bunch of values. 0.5. 19. Okay, that's not the sweet spot. 0.6. 16. 0.7. 14. Okay, 0.8 we know it's 9. Sorry, 12. Yeah, it looks like 0.8 is actually the sweet spot where you get about 12, and then it's higher either way around. It's clearly unstable when W is greater than 1. Okay, that gives you a value. Okay, it's not a number. Okay. Okay, any questions on this? Okay, so that's pretty much what we have for solving system of linear equations using computer methods.